Hi friends, this is the 8th lecture in the lecture series for the preparation of GATE in mechanical engineering, and today we will be dealing with a concept called lumped capacity model. Lumped capacity model. And for this case, let's suppose two examples or two cases. That is, first one, that is periodic cooling or heating occurring in IC engines, and second one, cooling of metal ingots during the quenching process. In these two cases, what happens that temperature will be a function of x, y, z and t, and where x, y, z are the spatial coordinates and this t is the nothing but time. Okay, so what we can see that temperature is function of spatial coordinates and the time. So this variation or the dependence of the temperature with respect to spatial location and time is nothing but unsteady state. So consider some this here in these two examples, the heat transfer that is occurring by conduction, and whenever there is the temperature that is dependent on the spatial locations and also the time, then that case is nothing but the unsteady state. And so for these two cases, the our heat conduction is nothing but unsteady state heat conduction. Since this unsteady state heat conduction is depending on the spatial location and the time, the solution or resolving procedure is very cumbersome. So we have to minimize the difficulty. For that, what we are doing is we are considering this temperature is function of time alone, and if we are considering this temperature as a function of time alone, then that simplified form will be called lumped capacity model. Okay, so what happens if we consider temperature as function of time only, that at a particular time instant, say t, the temperature of the body will be all over the body will be same. So this is nothing but uniform temperature condition. So basic assumption of our unsteady state heat conduction into lumped capacity model is nothing but the uniform temperature condition. So I will explain this in detail. That consider some plane wall like this, and this is having a length or width or the thickness L, and at this surface we are having temperature Ts1, and at this surface we are having temperature Ts2. Consider some fluid is flowing over this side of the plane wall, and this fluid is having some temperature T infinity, and the convective heat transfer coefficient is represented as H. Suppose Ts1 is greater than Ts2 is greater than T infinity. So if we consider the energy balance at the surface 2, we can write energy, or we can write heat or rate of heat arriving at surface 2 will be equal to rate of heat leaving from surface 2. So this is simply an energy balance of the flow, particularly the heat flow. So we can represent it in our mathematical forms that Ka Ts1 minus Ts2 by L will be equal to Ha Ts2 minus T infinity. And some mathematical manipulations, we can write Ts1 minus Ts2 by Ts2 minus T infinity will be equal to T infinity will be equal to Ha by L by Ka. Okay, so we can, sorry, there is a slight error. HA by Ka by L. So we can rewrite this equation as Ts1 minus Ts2 by Ts2 minus T infinity will be equal to L by Ka the whole divided by 1 by H. So this L by Ka is nothing but the conductive thermal resistance of plane wall, and this 1 by Hi is convective thermal resistance. So this ratio of conduction resistance and the convection resistance is a dimensionless number, and this dimensionless number is nothing but the Biot number, that is represented as Bi, Biot number. Okay, so if suppose this Biot number is somewhere around the value 0.1, what happens in this particular equation as Ts1 will be equal to approximately equal to Ts2, that is uniform temperature condition, and this uniform temperature condition means lumped capacity model is valid. So the basic condition necessary for the lumped capacity model is uniform temperature, and the condition that is sufficient or necessary for the lumped capacity model is Biot number approximately equal to 0.1 or Biot number less than 0.1. These are the two conditions for lumped capacity model, which is a simpler model of the unsteady state problems. So that's it. So along with this dimensionless number Biot number, we have to consider some other dimensionless number, which is Fourier number, which is represented as Fo, and which is simply the ratio of ability to conduct energy divided by ability to store energy, and this is nothing but the Q dot by du by dt, where u is the internal energy. So we can write this equation as Ka by L into delta T divided by rho Cv into delta T by T. Okay, this T is nothing but time, and this is letter V for volume. So we can write this equation as, cancelling delta T, we can write this equation as K by rho C into A by L into V into T. So this K by rho C is nothing but alpha, and here this A is proportional to L square, and this V is proportional to L cube. So we can write this as alpha into L square T by L into L cube. So this Fourier number can be represented as alpha, cancelling these equations, alpha T by L square. So this is nothing but the Fourier number. So the dimensionless numbers that are present in the Biot lumped capacity model is Biot number, which is HL by K, which is nothing but R conduction by R convection, and is Ts1 minus Ts2 by Ts2 minus T infinity, and the next one is the Fourier number, which is alpha T by L square, which is nothing but the Q dot by du by dt. Okay, so in these two cases we can see some letter L, and this letter L is nothing but the characteristic length. It is not a characteristic length or characteristic dimension. It is not a length as of physical sense, and this is a characteristic dimension, and this characteristic dimension will be different for different geometries. As examples, for cylinder, this characteristic dimension will be r by 2, and for sphere this characteristic dimensions will be r by 3, and for a rectangular plane this characteristic dimension will be L by 2, and for some cubical geometry and this characteristic length will be L by 6. Please note this characteristic length which is important, and then only we can analyze the entire body using this lambda capacity model. Okay.